Welcome to NASA's Jet Propulsion Laboratory. I'm Jane Platt with the Media Relations Office. Well, the Mars Curiosity rover is settling in well into its new home on Mars, and I guess we could say it's really on a roll right now. We're going to be hearing from a panel of scientists and engineers to tell us what's going on. But first, I did want to mention that today has been declared Space Day by California Governor Jerry Brown, who will be visiting JPL and meeting with the rover team later on. But in the meantime, we're going to start with our panel, and we're going to introduce them. First of all, we have Michael Meyer. He's the lead scientist for the Mars Exploration Program, NASA headquarters in Washington. We have Pete Teisinger, the MSL project manager for the Jet Propulsion Laboratory. And we have Roger Wiens, principal investigator of the ChemCam instrument, Los Alamos National Laboratory in New Mexico. Matt Heverly. Matt Heverly is next, and he's the lead rover planner for, he's here at JPL. And Roger Wiens, then, is the principal investigator at ChemCam from Los Alamos in New Mexico. And we have, last but not least, Joy Crisp, the deputy project scientist at JPL. We're going to start things off this morning with a special announcement from Michael Meyer.
Well, thank you. Actually, before I make the announcement, which I think all of you will enjoy, I would like to show you a short video. This video was made on the eve of the arrival at Mars of Mariner 9. This was in November of 1971, and in the video you'll see a couple people you might recognize, like Bruce Murray and Carl Sagan and Ray Bradbury. So if we can look at that video.
I was hoping that during the last few days, as we got closer to Mars and the dust cleared, that we see a lot of Martians standing there with huge signs saying Bradbury was right. Or even Clark. And I have brought along today, I'm going to keep this short because I'd much rather listen to our scientific friends here today tell us about what's coming up this week. But every time I get a group of people together and have them trapped in a hall like this, I bring a poem, see? And you can't escape me. But luckily it's a short poem, but it sums up some of my feelings on why I love space travel, why I write science fiction, why I'm intrigued with what's going on this weekend on Mars. And part of this has my philosophy about space travel in it, and if you'll permit, I'll read it to you. It's very, very short. The fence we walked between the years did balance us serene. It was a place half in the sky where in the green of leaf and promising of peach, we'd reach our hand to touch and almost touch the sky. If we could reach and touch, we said, it would teach us not to, never to, be dead. We ached and almost touched that stuff. Our reach was never quite enough. If only we had taller been and touched God's cuff, his hem, we would not have to go with them who've gone before, who, short as us, stood tall as they could stand, and hoped by stretching tall that they might keep their land, their home, their hearth, their flesh and soul. But they, like us, were standing in a hole. O Thomas, will a race one day stand really tall across the void, across the universe and all, and measured out with rocket fire, at last put Adam's finger forth, as on the Sistine ceiling, and God's hand come down the other way to measure man and find him good and gift him with forever's day? I work for that. Short man, large dream. I send my rockets forth between my ears, hoping an inch of good is worth a pound of years. Aching to hear a voice cry back along the universal mile, we've reached Alpha Centauri. We're tall. Oh God, we're tall.
And today, Sol 16, we have the first roving astrobiology rover on Mars. And we have truly extended our reach and touched another planet. Today would have been Ray Bradbury's 92nd birthday, but he has already reached immortality with hundreds of short stories he's written and nearly 50 books. His books have truly inspired us. The Martian Chronicles have inspired our curiosity and opened our minds to the possibility of life on Mars. In his honor, we declared the place that Curiosity touched down to be forever known as Bradbury Landing. I kind of like the name. For one, it was the majority vote of the science team having been inspired by Ray Bradbury. Landing is actually an event, it's not an object. Also, it harkens back to the time when ships landed on the shores of other new worlds to explore. And this place might, in fact, with its water reference, be even more apropos. So I would like to relay to you one of my favorite scenes from the Martian Chronicles, and that was when the humans peer over the rim of one of the Martian canals. And there they see reflected in the water Martians and themselves. And so as we look forward to one of those days, I would like to now turn it over to Pete Tysinger, who will tell us about our intrepid Martian, the Rover Curiosity.
Thank you, Mike. I would like, before I start, to give a small hand of applause to Ray Bradbury. He was a friend of JPL as well as of the Total Space Program, and several people, including myself, had the honor of meeting him, and so very apropos gesture. You are looking here today at a very smiley, ecstatic project manager. We have completed 16 sols on the surface, and everything has been going extremely well. I mean, really extremely well. We have no anomalies or other issues that we're working, with the exception of the REMS wind sensor anomaly, which is still in work. And if I could have the first slide, please. I'd kind of like to take you back to the day before landing. I think Richard Cook sat on this stage and talked about what the near-term plans were going to be after 10:31 on that Sunday evening, and I'd like to kind of let you know what's happened. In the early first week of the planned activities, we were going to do the high gain antenna deploy, mass deploy, instrument aliveness checks, acquire a panorama. We had a quiet day planned, and we were going to start, and then a few days later finish the flight software change to surface load. And you notice the check marks because we've successfully completed all those activities, basically on plan. Next slide, please. And this was kind of the longer view going forward. In early August, we were going to get the first images and finish the engineering checkout, and we've completed that activity. In mid to late August, we were going to complete the payload checkouts, and we've done that. And we're going to check out the sample system, and we have not quite completed that work. We have done a short drive today that Matt will talk about in a second, and with that activity, we have completed the characterization phase 1, both A and B. If you recall in that plan, there's going to be an intermission between Cap 1 and Cap 2, and that is going to take place. And that intermission is likely to be a little bit more extended. And so rather than do the surface sample checkouts and then the first drive, I think the scientists have decided we're going to take a little bit of an extensive drive, since we now know the system works well. And then we will complete the sample system checkouts later in August. We still ought to be able to complete a scoop sample in mid or late September on plan, and the first drill symbol in October and November. So right now, a little bit more intermission, a little bit more science from that, but we're basically on plan with what I like to repeat as an extremely well-behaved flight system on Mars. And Matt will tell us about today's drive.
Thanks, Pete. So let's get straight to the good stuff and put up the image from today, the very beautiful image. So I'm pleased to report that Curiosity today had her first successful drive on Mars. So this drive checkout, coupled with Yestersol's checkout of the steering actuators on Sol 15, means that we have a fully functioning mobility system on our rover. And in this image, you can see our touchdown point. You can see the tracks driving away from that location, as well as the scour marks to the right and the left of the rover's initial position. We drove forward, did a turn in place, and backed up. And you can see that the soil underneath the rover, it kind of confirms our expectations that the soil is firm, great for mobility, we're not seeing too much sinkage, and that we should have smooth sailing ahead of us. I've also got another graphic showing the animation of the drive today, if we can move to that. So this is our simulation and visualization tool, which shows our first drive. So we initially bumped forward 90 centimeters to image the wheels, and then drove an additional distance to total 4.5 meters, where we did our first turn in place. And you can see we're imaging every once in a while to look at the wheels as we're driving to inspect them and check them out, turning half of our 120-degree turn, turning the remaining distance, and then backing up 2.5 meters. So this final location places us in a good spot to do some good science here. We've got the Goldburn scour off to the right side of the rover where we can view it with the ChemCam instrument and the other instruments. The key things about the drive today were that we were able to do one full revolution of the drive actuators in the forward direction. We were able to turn and see that the inertial measurement unit telling the rover how its heading is changing is working properly, and we were able to back up another full revolution of the drive actuators. So we were able to see motor currents, we were able to get the data, and everything looks perfectly nominal. So we're very excited to have this kind of milestone behind us. We see that the system is performing very well, and we're in a great place to do some science. So with that, I'll pass it over to Roger.
Thanks, Matt. Exciting. So I'm going to talk about the checkout of the ChemCam instrument and some of the first science with it. The ChemCam is the laser instrument which fires high energy pulses at targets up to almost 25 feet away. That produces plasmas that provide chemical composition of the samples for us to understand. So we're going to cut to a video here which will show a demonstration before we integrated this instrument onto the rover. So here is the mast part of the ChemCam instrument. You see a 4.5-inch telescope there. The laser is right behind, and we're going to show a little demonstration where this instrument is going to be used to fire at an iron pyrite target about 8 feet away. So we're setting it up here. The laser beam is invisible, but you actually see the plasmas, first at 3 hertz here and then at 10 hertz. So you'll see how it can shoot, and then we just show a still image of the plasma so you can see what it really looks like. And this test was done at terrestrial pressure. It was done in Los Alamos National Lab, and the plasmas are more confined in a terrestrial atmosphere than they are on Mars. And so if we show the next image, you'll actually see the difference. So on the left, you'll see what a plasma looks like in a terrestrial environment. But this was in a chamber, and so then we evacuated it down to Mars pressure, which is about 1% of Earth's pressure. And on the right, you can see the size and brilliance of the plasma at Mars pressure. And so on the right is what's actually happening now on Mars. And as you know, the short of this is that we're getting great signals so far. Basically, ChemCam also includes a remote micro-imager. So this imager is designed to take close-up, high-resolution images to provide the context for these small analysis spots that we hit with the laser. But it can also image other areas as well. So until we pull out the Mastcam 100 and start using that, this is the highest resolution imager on the rover for right now. Basically, in the next image, we'll show the rock that we first analyzed on the surface of Mars. This was a rock called Coronation. It was selected because it was at a nice distance from the rover. It had a nice flat face. The rock itself is about only 3 inches across, and it's about, about 8 feet from the instrument. And so we sent up the commands on Saturday night, and the spectra came back early on Sunday morning, and we had a very excited team to look at this. And actually, the way we did this, we actually took an image the day before and then repointed just slightly. So the image you see on this picture is just a little bit off, but the next day we got it right in the middle, and we show a little inset of where it hit on the rock. And I'll show another one like that a little bit later. But the next slide we'll show is actually the spectrum from this rock. In short, we got excellent signal. We actually saturated one emission line oxygen just slightly, so that just shows what good signal we're getting from Mars. So the spectrum consists of 6,144 channels that span the wavelength range from 240 to 850 nanometers. And so that covers the ultraviolet with one spectrometer, a violet and blue range with another spectrometer, and then the visible and near infrared range that our eyes see with the third spectrometer. And so it covers all the rainbow colors plus a bunch on both sides. And so you can see labeled on there a number of emission lines that represent different elements, and so those are the things we look for. And so we can see the major elements on here: oxygen, silicon, magnesium, iron, sodium, potassium, calcium, but there's also minor and trace elements that we can really pick up with this instrument. And so the inset on the upper left actually shows titanium and manganese, which are quite lower in composition. And also, if you'll look, you can see lithium pointed out as well, and that's probably less than 50 parts per million. So there's a lot of detail we can get from this instrument, and so we're really excited about that. Just one more thing about that is the inset near the center, which shows the peaks of hydrogen and carbon. The carbon peak on the right of this inset is from the atmosphere, so there's nothing real big there in terms of findings. The peak on the left showing hydrogen, this is actually a sequence plot which shows every single laser shot as a separate spectrum, and we did 30 shots here. And so the first shot is shown in the white, and that curve shows that we actually had hydrogen on the first shot, but then it went down. We could barely see it on the second shot, and then it went away. So it shows us that on the very surface of this rock, we had hydrogen. Another thing that we saw on the surface was an enhancement of magnesium. So we saw this on Coronation. We also saw this on all of the samples we've looked at so far, including the calibration target on the rover. So this may be indicative of something from the dust. We've got to look into this a little bit more. Okay, so after this rock, we kind of told the science team that they were free to start choosing some targets, and they went and selected the Goulburn scour. This is the area where the rovers, or the Sky Crane's thrusters, actually sort of dug in a little bit with the blast, and they uncovered a small rock outcrop, which is of interest because of the way it looks. It looks as if it may have some little layers in it, and it's bedrock. So if we can go to the next image. This image shows a Mastcam 34 image in the center, and it is labeled with the locations of the remote micro imager, that's ChemCam's imager, pictures that were taken, pictures 1 through 6. These are the little round images that show high resolution. And so we targeted this for both imaging, and we targeted Goulburn locations 2, 3, and 4 for the laser as well. And so we shot the laser at the center of these images. And so the results we got there are pretty consistent with what we saw on Coronation. The Coronation results really look like a basaltic composition, and so that's not too surprising for the surface of Mars. We know that basalt is the major igneous rock on Mars. The fact that Goulburn, which looks a little bit sedimentary, shows a basaltic composition is also not too surprising, because when we look at this close up with RMI, the remote microimager, we see that there are clasts or rock fragments that look like they were probably basaltic as well. And so if this is a sedimentary rock, it incorporated and loosely cemented some of these basaltic rock fragments. Some of them are angular, so they look like they didn't get much altered, and some of them are a little bit more rounded. That's kind of the story. We've also shot a couple of other rocks. One of them did give a different composition, but it's still consistent with an igneous rock. It looks like we hit more of a mineral grain, potentially plagioclase, but it's still consistent with a basaltic composition. But because of the small spots that ChemCam can shoot, we can get single mineral grains if it's a larger grained rock. What we'll need to do is move towards doing rasters and line scans, so we get more analysis spots on single rocks so we can really tell. So we're still working on checking some of those things out. So I'm just going to show a final image, which is actually the Goldburn number 3, and this is an animation that just cuts between a before and after image that we took with the micro imager, showing what the rock looks like just before and just after shooting it with the laser. And so you can see how we can see where the laser shot. So there you have it. And we're going to be looking forward to doing more, lots more science with the ChemCam instrument, but we're excited that it's looking great so far. So I'll turn it over to Joy Crisp, who's going to talk more about the overall science status of the mission.
Thank you. So I'm going to go over some more specifics about what we've done for science and what's coming in our science plans. The engineering cameras are now fully checked out and being used to measure atmospheric dust, winds, and clouds. We've taken color images from MOLLE and Mastcam. We've also performed thorough checkouts on 8 of our 10 scientific instruments. As we've described in previous press briefings, the RAD radiation monitor, the REMS weather station, the DAN neutron subsurface sounder, and ChemCam laser spectrometer and imager are already taking scientific measurements. The DAN team is busy assessing their first active measurement that they reported in the previous press conference. ChemCam team is poring over their data, as you heard from Roger. And we've got several days of all-day, all-night weather readings that we're studying. And we've partially checked out the remaining 2 instruments, our analytical laboratories, SAM and ChemIn. So we're about to go into this intermission period, which we have 3 major activities going on in this period. So we'll have 2 separate days where we do some SAM atmospheric checkouts. And first time we do that, that will be the first turn on of SAM's pumps, quadrupole mass spectrometer, and tunable laser spectrometer. So that will be very exciting. We will have a campaign to do some of the advanced capabilities of Mastcam, like the precise focusing over the range that it can focus on, taking long-range 3D images by positioning the rover at different parking spots and using those spots like different eye positions to get the 3D range information and check that out. And then also, thirdly, the ChemCam laser spectrometer, we're going to do some more characterization of that to understand how well the optics are aligned and how sensitive the spectrometer is. So after the intermission, then we're currently planning to drive towards Glenelg, which is 400 meters to the east. That's the triple junction that we've shown pictures of before. And we're thinking of spending a few more days before we start driving towards that, examining the scours, these scours from the sky crane thrusters, using Mastcam, ChemCam, and DAN. Okay? Now, on the way to Glenelg, we'd like to stop as soon as we encounter scoopable fine material to get going, testing out the sample handling system and getting sample into SAM and ChemIn. The first material would be scoopable fines, and we would be trying to clean out that sample acquisition, the scoop and sample handling system by doing that several times, just tossing it out on the ground and then taking a sample to put into SAM and ChemIn. We might likely hold off on doing our first contact science with APXS and MOLLE until we get to that area, but that is to be determined. We may encounter something that we want to do that on before we get there. This stop at the scoopable fines is likely to take a few weeks. So all of this is still fairly uncertain in terms of the timing. When we finally get to Glenelg after doing that, we want to study the outcrop there and take a look at the contacts between the 3 different terrain types. And maybe there is where we would decide to do our first drilling into rock. And after Glenelg, we head for Mount Sharp. And that will be a much longer drive with probably some few brief stops along the way. That's going to take several months before we get to that point. That's pretty much sums up what we've done, what we're doing. We really are ramping up from having the initial checkouts under our belt, and now we're doing very complicated activity plans each day and working hard on these strategic plans, what the order of activities should be and how long everything's going to take. So I'll hand it back to Rosemary for Q&A.
Okay, thank you, Joy. I'd like to start with a couple of questions here in the auditorium at JPL. We do have some reporters on the line, so we will get to those as well. If you have a question, please raise your hand high and wait for the mic to get to you, and then identify yourself, your name, and your affiliation. So do we have a question? Yeah, let's go in the third row right here. Yes.
Steve Futterman from CBS. Pete and Matt, I guess, or anyone who wants to chip comment. How significant is this landmark moment, the first drive, as short as it might have been?
But it couldn't be more important. I mean, we built a rover, so unless the rover roves, we really haven't accomplished anything. And so, yes, tremendous. And the fact that we were completely exercised it and everything was on track is a big moment, very big moment.
Yeah, I mean, we've got an amazing team that built this very capable rover. We had a lot of confidence that it was going to work, but you're always a little nervous until you get the data. So seeing that, everything was nominal, as Pete said, all the steer actuators, all the drive actuators work, all the instruments, the inertial measurement unit that tells us how we're turning all works. We can now kind of focus on moving to checking out higher level behaviors for the rover, which will allow us to drive further every day, allow us to do kind of autonomous terrain assessment, visual odometry to more accurately track where the rover goes. So we're on pace to having this amazingly capable rover that can traverse over to the base of Mount Sharp.
If I'd like to add just one other thing is, as you know, in the past when the project got into difficulty, one of the principal developmental issues we were working was with the actuators. And I think we need to recognize the actuator, Aeroflex actuator supplier and the actuator team here at JPL for what has been perfect performance so far on Mars. And it's not just the drive, it's also the arm and the mast and the high gain antenna. So far they've been just perfect over what is a very demanding environment. So those people need to be congratulated for that.
Okay, do we have another question here at JPL? If so, raise your hand. Let's go to the phones then, and we can always jump back here. The first question on the phone will come from Eric Hand at Nature. Go ahead, Eric.
Hi, thanks. Yeah, my question is for Joy Crisp. Hi, Joy. If you could give me a more specific timeline for the intermission, when, I guess, in terms of the specific sol in which the activity would happen, can you say when intermission would begin, when the first SAM atmospheric study would happen, and then when you might begin the drive to Glenard?
Well, all I can say is we're beginning it tomorrow, and it will span several days, and we can't know exactly what days we're going to do each thing. I believe that we're going to be trying to do the first SAM atmospheric test on Sol 18, but these things are subject to change as we do the planning. Things can change the order in which we do things. So the best answer I can give you is in a period of a few days, and like on the order of a week is what that intermission will last. And that's the best I can do.
So on the order of a week later, you might begin the drive to Glenard?
On that order.
And as a quick follow-up, how quickly do you think you might be able to have a trace gas result from SAM? Is that something you'll be able to know in a day or two?
The first atmospheric measurements done by SAM are really checkouts, not so much meant to be definitive measurements. So they really need they're not optimized yet for making good measurements, and so you'll just have to stay tuned for what they can say about those measurements. But really they're meant for just the first checkouts. First one is very short integration time. They will learn from those how to set up the measurements for a very good, careful analysis.
So it's not possible that you could maybe see signs of methane in this first checkout?
I will leave that to the SAM PI to report after he sees his measurements. But
Okay.
for now, it's really meant to be a checkout.
Okay, thanks, Joey.
Okay, we're going to take another question by phone from the LA Times, Amina Khan.
Hi, thanks for taking my question. I just wanted to see if you could talk a little bit more about Glen Elg and the three types of terrain there. You know, what do they look like? Is it just that layered bedrock that you guys are looking to drill? And, you know, before you get there, is there any sort of sense of what the story is geologically there?
We have seen very many interesting cartoons by the science team trying to look at different possibilities for what the geologic situation is there. And so they're really in the hypothesis stage, and it's too early to say. What we can see is different textures to these terrains in terms of cratering and the looks to them, their albedos. It's nearby, and it looks like we should be able to encounter bedrock there. So that's a really good reason for going there is to be able to examine three different materials that are in place that look like we could sample rock. Not much more I can say about it at this point, but that it does look intriguing. I don't know if anybody else on the panel wants to add to that.
Okay, well then let's take our next question again by phone. That's Irene Klotz from Reuters.
Hi, thanks very much. I have just one quick follow-up about the drive. Just wanted to know if indeed it took 30 minutes, as we were told yesterday that would be the likely duration of it. And then I have a couple questions about ChemCam. Thanks.
So the drive started local solar time at 13:32, which was 7:17 a.m. here, Pacific Daylight Time. And with all the imaging, it took roughly 16 minutes. And the majority of that time is spent taking the images. The rover actually probably only drove for 4 or 5 minutes of that motion.
Thanks very much. And for Roger, one of the things I think you all had talked about earlier with ChemCam is you were curious if you were going to see different spectra as you pulse deeper into the rock, and I was wondering if you did see any composition changes. And then I think I might have, I wasn't sure about this, but is coronation actually at the Goldburn Scour, or was that in a different location? Thanks.
No, I'll answer your first question, or your last question first. Coronation was not part of the Goldburn Scour. It was just sort of ahead of and a little bit to the right of the rover where it was sitting when it landed. The Goldburn Scour was off to the left. And so if you look back at the image of Coronation, you'll actually see the rover's shadow in it. And that's sort of looking to the forward side of the rover. Let's see. The other was about asking whether we were seeing differences in the spectra as we dug down into the rock. So the little inset of the spectrum did show the hydrogen at the very surface. So of course the surface is one thing we're interested in, and we'll be looking into that further. There was a hint of some other variations in one other measurement we made. But this can be, say, a transition between looking at one mineral grain to another. So we have to look at that a little bit more.
Okay, before we go back to another phone question, just want to make sure anybody, reporters here at JPL who have a question, just go ahead and raise your hand and we will get to you. But in the meantime, let's take a phone question from Leo Enright at Irish TV.
Thanks very much, Jane. Just a quick question about coronation and the spectra. You said that it had a basaltic composition. So, I mean, what do you say? Are you saying this is basalt, Jim, but not as we know it? Or is this standard basalt, and can you make any comparison with, where on Earth you might find similar basalts, given that you seem to know so much about this already, thanks to this instrument?
Yeah, thanks. We're still working on the calibrations in a big way yet on ChemCam. We have a number of different types of calibration we have to do. First of all, wavelength calibration. This is this spectrometer has much higher sensitivity to the wavelength than anything that we've used in this spectral region before, and so we're working to make sure that that is characterized. I mean, the wavelength shifts just a little bit when the rover changes temperature just slightly during the day. And so we're working on that. We also have a spectral library that we built up back here before we sent the instrument off. And so we have those to compare with. But right now all we're doing is looking qualitatively at that spectrum and sort of matching it up against a spectrum that we have from the laboratory, and it just looks like some of the basalts. We're going to get into the quantitative aspects in a little bit, but I also want to say that ChemCam is a bit less quantitative actually than the APXS instrument on board for many elements, and so we're also looking forward to when APXS gets deployed on the arm, and when we can make some cross calibrations, which will make us more certain of our compositions as well. These two instruments really complement each other very well. ChemCam gets some elements very sensitively that APXS does not, and APXS tends to have more accuracy overall than ChemCam. So it's a great duo to have.
Our next question is going to come from Ken Kramer at Spaceflight Magazine. You there, Ken? Hello, Ken. Are you still there? If so, you can go ahead and ask your question. Okay, I guess, yeah, we'll come back to Ken if he reappears. The next question is going to come from Robert Perlman at collectspace.com. Robert, you there?
I am. Looking at the tracks, can you quantify how deep or how shallow the track marks are? And if, for example, if a good windstorm came by, would they just be blown away? Or what does that tell you about the nature of the land that you landed on? Can I have a follow-up?
I can answer maybe just how deep we sink. So we've got the cleats, which are about 1 centimeter or so tall. And what happens is we dig into the terrain with the cleats, and then the ground pressure is absorbed by the rest of the wheel. And we don't see much sinkage beyond that, where if you were driving on really soft sand, you would see significantly more sinkage. So we can tell just from the properties of looking at these tracks kind of how firm the soil is. But I don't think I can necessarily answer a question about the dust and how they might get covered up. Maybe Joy?
Well, it'll depend on what the winds do and whether there's fine material that'll get deposited on these tracks or not. I think, if I'm not mistaken, the tracks should be somewhat similar in depth to MER tracks. So there still could be a difference in the material properties here. But if you treat them as MER tracks, then there were times, it took many sols when the tracks would get covered and start to disappear. So I don't expect that this would happen rapidly, but maybe after many months or years, it get harder and harder to see these tracks.
Okay.
Thanks. And just a quick follow-up with regards to Bradbury Landing. Is it defined by the borders of Curiosity's wheels where it sat, where it landed, or does it encompass this whole area where you're now even sitting now?
Well, we're actually thinking of using the wheel marks as the corner post for Bradbury Landing.
Okay, great, thanks.
I'm told that Ken Kramer of Spaceflight Magazine has reappeared, so go ahead, Ken.
Okay, I'm here. Can you hear me? I hope we didn't get disconnected again. My question is for Roger Wiens. I wonder if you could talk about how many targets in a day can you analyze with ChemCam? I understand it's 14,000 overall, but I was wondering in a day how many can you analyze?
Yeah, so that 14,000 number came from looking at the number of days or sols that were going to be on Mars in the nominal mission, which is 700 some, and assuming that a maximum that we would possibly do would be 20 analyses per day. And so that's how we came up with that. Now it's going to be a long time, or it could be a while anyway, before we get to do 20 analyses in one day. But if we arrive at a new site after driving some distance, and you can imagine an outcrop in front of us, we could perhaps target something close to that. It really depends how crafty and how skillful some of our uplink people get at devising these sequences. And they're coming up to speed very nicely.
Okay, and I was wondering, too, after you get the data, how quickly are you able to analyze it and decide, what you're seeing?
Yeah, so the process, once the information comes down, we have a role called a payload downlink lead, and so that person is responsible on our ChemCam team for pulling the data over onto a computer and starting to first of all check out what files did we receive, and then secondly, are they looking okay? And so we look at the images that we received, and we look at the spectra that we received, and we look at other things such as we usually take a non-laser dark spectrum as well to subtract the background. All of those things get pulled together, and then within about a couple of hours, they've usually gone through and cataloged what we've seen, and we get ready to present that at a science kickoff meeting within about 2 hours of the downlink. And then we usually do more analysis after that, but that's the initial.
Thank you.
We're going to take a question now from space.com and Mike Wall, and I see we do have a question after that from JPL. Go ahead, Mike.
Yeah. Oh, yeah, hi. This one's probably for Matt. Do you guys have any idea, once you guys start to actually drive, make your first big drives, how long are those first drives going to be when you finally head out from the sort of landing site where you are now and head toward your first big science target? Like, are those going to be 10 to 20 meters like I've heard before, or do you guys have a little more confidence now that maybe you can make some longer drives?
That's a good question, Mike. So we'll start out with fairly modest drives in the 10-meter range. And then, as I mentioned before, we're going to do a couple checkouts. We're going to check out the autonomous ability of the rover to image obstacles and identify hazards so that it doesn't, it keeps itself safe. We'll check out visual odometry, where the rover takes a couple of images and is able to calculate how far it moves so we can see if we're slipping and embedding in the terrain. And we're doing that on Mars because we've never done that image processing on board the software using images coming from Mars. It's different lighting, it's different terrain, so we just want to make sure it's all working as we expect. Once we get that functionality checked out and we have confidence in it, we'll start expanding the drive distances. We'll go to 20 meters, 30 meters, 40 meters. And 40 meters is kind of the edge of our NavCam horizon that we can see right now. That's where we get good stereo data with these NavCams that we're taking. And then as we continue to have more and more confidence in the system, we'll extend those drives and we'll start driving beyond that NavCam horizon out 50, even up to potentially 100 meters or so per sol.
We're going to jump back to JPL. We have a question from a woman in the row there. Please state your name and affiliation.
Amy Johnson, KCBS TV. I think my question is for Matt. And looking at the screen here, this photo, I can clearly make out the tracks, but can you explain a little bit more about what we're actually seeing in this photo?
Yeah, so this is a very historic photo. There's only one place on Mars where you start your tracks, and you can see exactly where we landed because you can see the tracks where we're starting. And then to the right of the tracks, you can see kind of two dark spots. Those are the scour marks from the landing engines. And then similar, you see them symmetrically on the other side, the two left marks. And then you can see in the tracks how we drive forward, and then you can see roughly a circle, which is where the rover did what we call its turn-in-place maneuver. So it steered all of its wheels, and then it performed a turn of 120 degrees, pivoting about that point in the middle of that circle, and then it backed up. One of the other things that we can point out in here is that we see different patterns in the wheels. We have intentionally put holes in the wheels to leave a unique track on Mars that we can use for that visual odometry, where we can, if we're in sand dunes where we don't have lots of rock features around us, we can use those patterns to do our visual odometry. The other thing to note in here is there's a small rock under where we landed on the right rear wheel. And when we did our steer actuator checkout, we saw some somewhat high currents, and you can actually see in the animation that the bogie, the suspension system at the back of the rover, kind of tweaks out to the right a little bit. And we were able to confirm that we were kind of on that 9-centimeter tall rock when we landed down. So this is great. We're able to see under the rover, see exactly what we landed on, and kind of correlate that to the engineering data we got from the Sol 15 steer actuator checkout. Did that answer your question?
It did. Thank you.
Okay, and that, it looks like we have time for one more question. Go ahead.
And a nice ending question. The President of the United States lauded JPL and Dr. Alachi. The Governor of California is going to be here today. Michael, if you wouldn't mind, everything seems to have been working perfectly up till now. It seems to be textbook. Give us an assessment several weeks into this now as to how your team is working. Your Seoul is a different day than the one that we're used to, and what the attitude is like now that you've captured the nation's attention and the imagination of so many with this rover.
The team is tremendously excited. Everything's working. We've kind of gone through starting in the middle of the night, going through daylight, and actually over the next couple of weeks we're going to move back to being on the night shift as the difference between Earth Day and Mars Sol shifts out of, from day to day night. But everything's working. The hard part is kind of dampening the excitement a little bit so that people get enough rest so that they are in it for the long haul instead of just waiting anxiously for each image to come down. But it is fantastic how well everything is working. And so everything that we've promised with this rover going to Mars and going to a place where we think is interactive with water, we have high hopes that this is going to really prove out this region and tell us whether or not it was ever potentially habitable.
And I wouldn't be doing my job if I didn't exercise a little bit of caution here. Okay? We are 16 days into a 2-year mission. Okay? We haven't put the arm on the ground yet. Okay, we haven't exercised the sample gathering capability, which is a key element of this rover science mission. So as good as it's gone and as wonderful as it is, we still only checked off about 2 of the level 1 requirement boxes: launch on time, land on Mars. Okay, and we got a long way to go before this mission reaches its full potential, But the fact we haven't had any early problem is in fact fantastic. But I just, managing expectations, right? And we got to keep doing this as the team has been doing, methodically, properly, prudently, so as not to get out of ourselves and cause ourselves our own headache. But as Michael said, so far it's been wonderful.
Science, engineering, enthusiasm, caution.
What more would you expect?
All right, well, that wraps up the Q&A portion, and thank you to our panelists. Immediately after this, we will replay the visuals from the news conference, and remember, a lot of information's online and images 24/7 at www.nasa.gov/MSL. However, in closing, we do have a short video clip from 2009 when Ray Bradbury visited JPL, and he was right here in this Von Karman auditorium. He was here to congratulate the team on the 5th anniversary of the twin Mars rovers, Spirit and Opportunity. And some of the rover drivers, they were very excited to meet him and wanted to express their gratitude to him for inspiring them. So we have a very short video remembrance of that day to share with you.
Having Ray Bradbury here was incredible because in particular for Mars, he really has been one of the voices from very, very early on for going to Mars and exploring Mars long before we knew how to do it. He was taking us there in our minds.
Let me introduce you to some of the other people who drive the rover with me.
Yes, sir. So our rovers look just like this.
When he came to the operations room and we showed him the model of the rover and the large-scale panoramic pictures that we've taken, the actual photographs of the surface of the planet, it was like watching him experience it as a child almost would experience it, just the wonderment. He has never lost that wonder for Mars that he's always conveyed in his books.
There you go. You're getting the hang of it already. We're going to have to hire you.
Showing him how we control the rover and using the simulator and letting him basically drive the simulated rover across the surface of the planet and letting him see the reality of that was very rewarding for us because we could tell how much it meant to him to see this that once that was only fiction, that partly because of his vision and his sharing that vision with us, that it's now become a reality and that we're actually there.